Hello mathematicians, welcome to Proof by Mathematical Induction. Mathematical induction is a method in maths which allows us to prove some conjectures, and it basically relies on us connecting one line of a proof to another line in the proof. So we have a strict pattern to follow if we're going to prove that conjecture. So step number one is always to understand what it is we're trying to prove. We don't have to call it a conjecture. We just have to make it clear what we're trying to prove. So what we're trying to prove here is that all the dominoes will fall if the first one does. We then have to show that it's true for the first case of interest. So for us that just means the first domino is able to fall. Then we assume it's true for some general case where n equals k. Now this will become a little bit clearer when we're actually dealing with examples, but what it's saying is, well, the first k dominoes will fall. K is just any number. But the key bit is that we show that if it's true for our assumption of n equals k, then it's also true for the next case. So that we can say, well, if k dominoes fall, the k plus 1th, the next one in line, will also fall. And if we can do that, then we're said to be able to have proven by mathematical induction that it's true for the first value of n, therefore by the fact that our first value of n could be k, then it's true for the second. And if it's true for the second, it's true for the third, and so on. So our conclusion, our logical conclusion by mathematical induction, is therefore all the dominoes fall. So that's our proof of the conjecture. Now let's look at a little bit more useful example. The mathematical induction questions that you face usually come in three types. So first one is proving formulas that concern sums. So the conjecture could be something like this, that 1 cubed plus 2 cubed, so you can see why this is in the series topic, all the way up to some n cubed equals this expression just here. So we could prove it for individual cases, but we want to prove that it's true for every case where n is greater than or equal to 1. So step one is show that it's true for the very first case, the first domino, if you like, in the series. So to do that, when n equals 1, the left-hand side is 1 cubed, and the right-hand side is this expression with a 1 placed in the position of n. So that comes out to be 1. So we know that this conjecture is true for the case where n equals 1. Then we assume that it's true for n equals k. So we assume it's true for any particular value or any general value k. So if that is the case, then if we assume it's true for n equals k, we're just saying this. We're replacing n by k. Now comes the hard bit, and it's the crucial bit. So we're going to show that if it is true for n equals k, then we're going to try to show that it must therefore be true for n equals k plus 1. So we have a pattern to this. So when n equals k plus 1, what does our left-hand side become? Well, it becomes all of that stuff up to k plus the next term. And we work on that with the aim of showing that it equals the form of the right-hand side. So we take all of this stuff here, which we've already assumed is equal to that, so that was our assumption, and we're adding that. And algebraically, we work on that so that we can make it look like this expression up here, where we write k plus 1 wherever we've got n. So you can see that here we could take out k plus 1 squared as a common factor for these two. So that's our half k plus 1 squared, that's like half n squared. And in here we've got k squared plus 4k plus 4. Now k squared plus 4k plus 4, of course, is k plus 2 all squared. So what we can see is that if we wrote n as k plus 1, then this is what it would look like, just that bit there. So the significance of that is that we've proved that it's true for n equals k plus 1, if it's true for n equals k. Now it just becomes a chain of logic. So we proved it was true for n equals 1, Therefore, by our step here, it must be true for n equals 2. If it's true for n equals 2, it must be true for n equals 3, and so on. So we've proven that it's true for all n greater than or equal to 1 by the process of mathematical induction. So it's a very powerful proof, but it does require strict adherence to the setting out. Now, let's have a look at another type of question, one concerning divisibility. So, what we want to prove could be something like this, that 3 to the 4n minus 1 is divisible by 80. So, show it's true for the first case. So when n equals 1, 3 to the 4n minus 1 is 3 to the 4 minus 1, which is 80. So obviously it's true for n equals 1. Now we then assume that it's true for n equals k. So setting out is slightly different here, but the logic is the same. So if it's true for n equals k, that means 3 to the 4k minus 1 must equal 80 times some integer. So there's nothing special about the letter m, it's just that m needs to be a positive integer. So in other words, 80 goes into 3 to the 4k minus 1 a whole number of times. Now we set about showing that if it's true for n equals k, it's also true for the subsequent case, n equals k plus 1. So when n does equal k plus 1, our expression becomes this, 3 to the 4 outside of k plus 1 minus 1. Now our aim will be to show that this thing itself is divisible by 80. So a common trick is first of all to break it up so that we've got our original conjecture repeated somewhere in here. So 3 to the 4k plus 1 is obviously 3 to the 4k multiplied by 3 to the 4, and we've still got our minus 1. But our 3 to the 4k from up here, we can see is going to be equal to 80m plus 1. So that's what we substitute. So 3 to the 4k becomes that, 3 to the 4 is 81, and we've got our minus 1 still there. Now if we expand those brackets out, we've got 81 times 80m plus 81 minus 1, and that gives us 80 outside of 81m plus 1. We're just taking 80 out as a common denominator. So again, what we can see is that when n equals k plus 1, we get a multiple of 80, so it's divisible by 80. So it's therefore true for n equals k plus 1 if it's been assumed true for n equals k. Therefore, by our mathematical induction, it's true for n equals 1, it therefore must be true for n equals 2, 3, and so on. So we have to wrap it up with this statement, and this statement is just not something we can ignore, because until we put that in, we haven't actually explained what the process is. Now, let's have a look at our last type, which is concerning inequalities, and these can be the trickiest when you are not thinking about what you're writing down. So our conjecture could be something like this. 2 to the n is greater than n squared. Now in this case, for integers greater than or equal to 5. So show that it's true for the first case. So that means for n equals 5, the left-hand side will be 32, the right-hand side will be 25. So clearly it's true for n equals 5. Now we then assume it's true for n equals k. So if it's true for n equals k, then we're saying 2 to the k is greater than k squared. And sometimes it's worth rewriting that by taking the k squared over, and so you can say that what's on the left-hand side is greater than what's on the right-hand side. If you subtract the right-hand side from the left-hand side, and you get an answer which is greater than or equal to 0. So let's try that approach. It's not necessary, but sometimes it lets people keep track of the progression of their answer. So, show if it's true for n equals k, it's also true for n equals k plus 1. So, when n equals k plus 1, our expression up here becomes 2 to the k plus 1 minus k plus 1 squared, which, if we expand it out, equals that. So again, trying to put things in terms of the original expression. Now, the reason for doing that is that we then progressively build, in a sense, the inequality. So our very next line says that this expression on the left, which is this one, is greater than 2 times k squared. So what we're doing there is using the fact that 2 to the k is greater than or equal to k squared to say that 2 to the 2k is greater than or equal to 2k squared, regardless of all of this other stuff. For what it's worth, notice that this other stuff, because it's squared, is a positive as well. Then, if we take this bit and rewrite it, so we've got 2k squareds minus a k squared minus 2k minus 1 when we expand that squared. So that simplifies to this. Now, even though this is equal to the line up above, we're still carrying on from this statement up here. So this statement up here is still greater than or equal to this one. And this in turn is greater than or equal to that, because we know that if we made that a plus 1 to complete the square and subtracted minus 2, this statement would be equal to that one, but again, by our logic, that is less than or equal to our original starting point up there. And this statement here is always going to be greater than 0 if n, or in this case k, the values of k that we're allowed to put in there, are greater than or equal to 5. So we just have to be a little bit switched on with inequalities, just to be sure that we're always establishing that one line, if we use this approach, is greater than or equal to the one below it. So finally, by mathematical induction, if we've proved that it's true for n equals, well in this case 5, not n equals 1, and having assumed it's true for n equals k, we've shown that it's true for n equals k plus 1, then we end up proving that it's true for all n. Now again, this should have said 5. We're proving it true for all n greater than or equal to 5. So have a little think now about what might be the key aspects of proof by mathematical induction so that you can get the process straight in your head, and then have a go at the questions in 6n. Now we could have lots and lots of these, but this will be enough to keep us busy and we should have our head around it by the end of this.